Hello everyone, this is Tuan, and in this video I will be talking about my model during the competition market scenario generator hackathon. A little bit overview about the competition. The competition was held by Professor Howley and her students. Uh, the competition main objective is to find the suitable generative model for financial time series including the log returns of five assets, their volatility for 5 consecutive days. It means that one point of simulation needs to be in the dimension of 1, 5, 10. The generated sample needs to be based on some condition C, which has two values, 1 or 0, during the time of crisis or regular market. And one remark about the competition is that the ratio between C values of C is 9 to 1 towards the normal condition. As for my model, I chose the conditional variational autoencoder. Instead of going through the basic principle of the model, I will just go through my motivations for current model or any further improvements based on the context of this competition. First, I noticed this is pretty well known that log returns and volatility have different range of values. -1 and 1 for returns and non-negative for the volatility. Next, log returns between assets have some linear or even non-linear correlation among themselves, and mean square error can calibrate the generated sample to the true sample. However, it lacks the ability to capture the distribution shape of the true sample. So with those motivation, some key points that distinguish my model with the normal vanilla variational autoencoder are first, I use different activation functions, hyperbolic tension for the returns, and sigma for the volatility. One can use the prelude activation as well. Next, I added a mean square error between the correlation matrix of the true and generate sample to somehow capture the dependencies between series. Mean square error was still among the loss functions as the Euclidean distance between the true and generated sample. However, I also added probabilistic distance using the KL divergence between the true and generated sample. For the imbalance problem, my approach is still very simple. I just put the condition flag C in the input of the decoder as the vector in R100 space. If you look closely here, we have the decoder condition input, which is this. I will repeat that value to be a vector with 100 components, and then I concat this vector with the random seek of the decoder, resulting in the vector with 105 components or concatenate 12, the node concatenate 12. And my rationale for doing this is quite simple. If you look at the bottom right figure here, you can see that most of the output or the simulation will depend on the weight matrix from this node, the concatenate 12. And remember that most of the components in this node are just like 1 or 0, right? So basically means that the weight matrix from this node will mostly be associated with the value 1 or the crisis market. Imagine if C equal to 0, then most of the weight matrix here will become useless because the input is 0. But if the C equal to 1, then the weight matrix here will act it to calibrate the normal simulation to the crisis simulation. And of course, this is the results, my results during the competition. The result is, I think, is pretty good, but one thing that that could be improved more is actually the histogram loss or the marginal loss. In the context of the competition, I think is the probabilistic distance between series, between true and simulated series. The difference between them are really high, really significant. So I have made some improvements. Some of the improvements including using the mean absolute error for the correlation matrices instead of mean square error, replace the KL divergence with the PSI or population stability index, which is like a symmetric version of the KL divergence. And so now we have for loss function. These first three are acted as the reconstruction loss, or the distance between the true and generated sample, and the KL loss. For the latent space vector, we need the latent space vector to be the standard Gaussian distribution. And these four loss functions will be taken average by a predetermined weight. For the improvement, I actually tested on another set. So I took five stocks data, split them into in sample and out sample with the same characteristics, the same rolling windows as the competition. In this setup, I was able to train with more number of epochs, as I suspect the PSI helped the generate sample from going far away or helps with prevent the model from being underfitted or overfitted. And also the number of tests is higher 100 test loops for this improvements only compared to only like five during the competition. And if you look on the table on the right here, you can see that the difference between across matrix and even for regular or crisis market difference are insignificant now. Like we have 18 to 20, we have 15 to 12, and so on. We have 0.36, 0.38, and so on, so on, so on. I mean, the difference between them are insignificant, so somehow indicating that the model was not being underfitted or overfitted. I actually have some ideas which is based on traditional econometric. My idea actually based on the symbol gauge Coppola model. The formula is right here is pretty standard for the financial time series models, but some outstanding points from this model is that with the second equation here, it is indicating that uh, volatility has some type of clustering of volatility shock, and their autocorrelation in the second equation. With the third equation or the Coppola function C here, they show the relationship and dependency between assets. So with that in mind, I am thinking that we can somehow use the Coppola function into the loss function, but instead of any Coppola function, we can just use the multivariate Gaussian distribution on the innovation. Again, the innovation is just we can have the innovation by dividing the returns by the volatility. That's it. However, in the context of this competition, after dividing the return with the volatility, we still have the vector of 5 times 5, which is difficult to calculate with the PDF function for the multivariate Gaussian. So I think that we can just take the mean over the assets dimensions, resulting in a 5 times 1 vector. And from here, we can calculate the values of the PDF function for the multivariate Gaussian distribution. For this improvement, I actually haven't got a chance to test it out, but but the results when I'm done will be put on my GitHub repo. I will put in my email as well. But anyway, thank you for listening so far. If you have any questions, even any idea that I can improve the model, please let me know. Just email me, and thank you.